So in video 1 we introduced acids and bases. So now we're going to talk about how to tell how strong an acid is. When an acid is dissolved in water, the proton, the H+, remember, is transferred from the acid to the water, as shown here, where the acid loses the H, so it becomes just the anion left, and then the water gains the H to make the hydronium. Okay, we just saw that in the first video. The conjugate acid and bases can then react with one another to form the original acid and water, the original base. Because this reaction can take place in both directions, we represent it with the double arrow, the equilibrium arrow that we saw in chapter 17. Right? Looks familiar. Each side of the equation is in competition for the proton in this situation. So if the water wins to gain the proton, we say that the acid has completely ionized or completely dissociated. So when the water wins and the acid completely breaks apart, this represents a strong acid. Remember, dissociated means breaks apart. If the conjugate base wins, then the reverse reaction is predominant, meaning that the acid will remain intact. So if the acid remains intact, then that represents a weak acid. So the difference between strong and weak. A strong acid contains a relatively weak conjugate base, one that has a low attraction for the proton. So that means that the acid will be more likely to dissociate into its ions and lose the proton, whereas a weak acid has a strong conjugate base, meaning it has a high attraction for protons, so the acid will not dissociate. So strong acid always breaks apart into its ions. Weak acid, usually just a little bit, will break apart into its ions. So here's a list of strong acids. There are 7 of them. Hydrochloric acid, nitric acid, perchloric acid, hydrobromic acid, nitric, sulfuric, chloric, and hydroiodic. If you need to pause to fill in the chemical formulas of those, I would do that now because you might need to recognize those later. So sulfuric acid is a diprotic acid, which means that it has 2 protons that it can get rid of, right? So if we get rid of one, if we take away a 1 to make the conjugate base, then we are still left with an H. So then what happens is that H, or that HSO4- loses the other H to then get just the sulfate from the sulfuric acid. And so that's just showing how it donates the 2 protons. Water is an amphoretic substance, which means that it can behave like an acid or as a base. It's the most common amphoretic substance of them all. And so this is illustrated by the ionization of water, where if we have 2 water molecules added together, one will gain and one will lose the proton. That just means it can act either way. It depends on the situation. So at 25 degrees Celsius, the actual concentrations of the hydronium and the hydroxide in pure water are equal to each other, and they're equal to 1 × 10⁻⁷ molar. Remember, the brackets mean concentration, just like they did in chapter 18. So that would mean that it's specifically talking about molarity here, moles over liters, okay? When we multiply the 2 together, we get Kw, which is the ion product constant. You just have to know that Kw is equal to 1 × 10⁻⁴, okay, when they're multiplied by each other. So in the top one I have hydronium, but in the bottom one we can just simply write the hydronium as H+, because that's the whole point, is it gained the H+. So I like to use the bottom equation better, where Kw, the value for Kw is the 1 × 10⁻⁴, okay? So make sure that you remember that. So we could just kind of take out that Kw part, where H times OH concentration is equal to the 1 × 10⁻⁴. And that's going to help us solve when we're using our ion product constant equation. So the meaning of the ion, or the Kw, in any aqueous solution, no matter what it contains, the product of the H plus and the OH minus must always equal that same value, the 1 times 10 to the negative 14. So this means that the ion's concentrations are inversely proportional. If one goes up, the other one goes down, right? That's what inverse means. So there's 3 types of solutions. If it's an acidic solution, that means that the acid is added to the water. The H plus concentration will be greater than the OH minus. So when I like to write it, I always like to say the concentration of the H plus that's ugly, sorry, is greater than. So I like to use that greater than sign, right? Than the OH minus. Ooh, that's crazy. And then if it's a basic solution, then that means that the base, the OH will be greater. So then you could flip it around and you could say that the OH concentration is bigger than the H plus, or the H plus is less than the OH. And then if it's neutral, then it's equal to each other. That means they're both the same thing, which is kind of how it was when we first introduced it. So the OH is greater than the H plus for that other one. Didn't try the brackets because it would just be even uglier. Sorry. So with this information and with our equation, we are going to be able to solve for either H plus or OH minus given some values. And then when we compare them, we compare the 2 values to see, is it acidic or is it basic or is it neutral? So the equation we're going to use is that Kw equation, where the concentration of the H plus times the concentration of the OH minus is equal to the Kw, 1 times 10 to the negative 14. Sorry, that was 1.0, wasn't it? For sig figs. Yeah. So for A, let's just not even think about B right now, okay? Let's just think about A. So for A, this is telling us that OH is equal to 1 times 10 to the negative 5th, okay? So that means I got to solve for the H plus. So to solve for the H plus, I'm going to take the Kw divided by the OH minus, because the Kw always needs to go in the numerator. So 1 times 10 to the negative 14 over the 1.0 times 10 to the negative 5. And when you divide that out, the H plus is equal to 1 times 10 to the negative 9 molar. Okay, so then now I have to compare H plus to OH minus. Well, which one is bigger? This is kind of tricky for people sometimes because we have to look at the exponents on the times 10, right? So when we look at the exponent on the times 10, we're comparing a negative 5 to a negative 9. And since they're negative numbers, that means that the one closest to 0 is going to be the bigger one. So negative 5 is closer to 0, so that means the OH is bigger than the H plus. So the way I wrote it right there, I have to put my less than. H plus is less than OH. So since the OH is greater, that means that the solution is basic. Okay. Now hopefully you didn't write that big so that you can do B now. So for B, we're done with A. Now we need to use B. So again, we're to find, using the equation, I'm going to need to find the OH this time because I'm given the H plus. So to do that, I need to take the Kw, the 1.0 times 10 to the negative 14, divided by the value given, which is 10.0. So when we divide that out, we get that the OH minus is 1 times 10 to the negative 15 molar. So that's not a correct sig fig, sorry. You guys are going to yell at me if I don't do that. My bad. There we go. So then that's our answer for the OH concentration. And then now we have to compare the H plus to the OH minus. I always like to put H plus first, honestly, because that helps me think of it. Comparing the exponents. I've got negative 15 on my OH, which is very, very small, actually. And then I have a 10, so I have greater than 1 here. So that's like extremely big compared to the OH. So that means the H plus is bigger. So since the H plus is bigger, that means it's acidic. Okay? So now let's do example 4. And then we'll be finished. For example 4, is it possible for an aqueous solution at 25 degrees Celsius to have a concentration of 0.01 molar for the H plus and the OH also to be 0.01 molar? Well, how we're going to do this with our equation that we had, right? We had the H plus times the OH minus is equal to our Kw, which is the 1.0 times 10 to the negative 14. Well, if I multiply these two numbers together that were given, and it equals to 1 times 10 to the negative 14, then yes, it is possible. If we multiply them together and it's not that, then no, it's not possible. Okay? So taking 0.010 times 0.010, when you multiply those out, you get, it probably doesn't show it in scientific notation on your calculators, but it's times 10 to the negative 4. Remember how we count that over? And that is not equal to what we said Kw is. So no, it's not possible. Okay, so that's all for video 2. We need to complete the acids and bases assignment and get that turned in. Make sure you check on the checklist when it's due. I will answer questions in class if you have any about this.